I want you to picture something for a second. Imagine the back room of your favorite seafood restaurant, like on a really busy Friday night.
Oh, that is always an intense scene.
Right. You've got waiters just rushing in and out, the smell of garlic and butter in the air, pans clattering, and back in the corner, just completely shrouded in the thick cloud of steam, is the dish pit.
Yeah. And from the outside, I mean, it looks like pure, wet chaos.
Exactly. It really does.
See, anyone who hasn't actually worked in one, it's just a messy, incredibly loud room where people are essentially, just spraying off plates with a high-powered hose.
It feels almost primitive, right, compared to the finesse happening out in the dining room.
Right, exactly.
But what if I told you that that humid, chaotic room is actually a highly regulated, high-stakes applied chemistry lab?
Oh, absolutely is.
And the margins for error between a perfectly safe, spotless dinner plate and a literal toxic hazard are just incredibly thin.
Razor thin.
So today, for this deep dive, we are unpacking an ISO-aligned research project authored for a commercial fish company. It breaks down their dishwashing efficiency, and we're looking at it alongside this massive data set directly from the FDA Food Code.
It's a lot of data.
It is. And what these sources reveal is this invisible molecular battleground hiding right under the commercial sink.
It's a fascinating hidden world.
Yeah.
And it requires this immense level of precision that we completely take for granted when we go out to eat.
Yeah.
At a commercial scale, you aren't just washing dishes, you are orchestrating a multi-stage chemical and mechanical process. And it's all governed by incredibly strict mathematical rules.
Because public health is on the line with every single cycle.
Exactly, every single plate.
Okay, so let's start at the very beginning of that cycle. Before a plate can actually be sanitized to protect public health, it obviously has to be physically clean.
Right. The soil, the leftover proteins, the heavy grease from that fried calamari.
Right, it all has to go. But there's a fundamental problem here that we all learned in grade school, which is that water and oil simply do not mix.
They absolutely oppose each other.
Yeah.
Water has very high surface tension, meaning its molecules like to stick tightly together.
Like magnets.
Exactly.
Mm-hmm.
And grease, on the other hand, is hydrophobic. It actively repels water.
Mm-hmm.
So if you just take a hose and spray water at a heavily greased plate...
The water just beads up and rolls right off.
Right. It doesn't actually penetrate the grease or lift the soil.
So how do we bridge that gap? Because obviously restaurants get the grease off the plates. The research report points to surfactants, which are surface active agents.
Yes.
But the way our sources describe their molecular structure is where it gets really interesting to me. I always just thought, soap is soap. But these molecules have very specific, almost opposing physical traits.
It's an incredibly elegant piece of chemistry. A surfactant molecule essentially has two distinct ends with completely opposite personalities.
Okay.
On one end, you have a hydrophobic tail. The sources describe this as an alkyl chain.
An alkyl chain.
Right, which you can visualize as this long, stringy tail of carbon and hydrogen atoms that aggressively avoids water.
Oh, but it absolutely loves grease.
Exactly. It wants to bury itself in the grease.
And what's on the other end of that stringy tail?
You have a hydrophilic head. This part is completely different. It loves water. In the specific formulations mentioned in our sources, it's often a sulfonate group.
Okay, so you have a molecule where one half desperately wants to bury itself in grease, and the other half wants to swim in the water.
Right.
So when this detergent hits the greasy plate in the main wash cycle, it's like a microscopic battle is taking place. The hydrophobic tails of the surfactant molecules, they just stab directly into the grease particle.
Because they want to escape the water at all costs.
Right. Meanwhile, the hydrophilic heads are facing outward, desperately bonding with the surrounding water.
And this interaction leads to what chemists call micelle formation.
Micelle formation.
Yeah. The surfactant molecules completely surround the grease particle in a three-dimensional sphere. They literally lift it off the surface of the plate and suspend it right in the middle of the water.
Oh, wow. So it's kind of like a microscopic game of Red Rover.
Huh. Red Rover.
Yeah, like a whole team of surfactants surrounds a blob of grease. They grab hands and literally yank it off the plate, trapping it in a little bubble so it can go down the drain.
That is actually a brilliant way to visualize it.
Yeah.
Yeah. They trap the soil in a protective sphere, a micelle, so it can't accidentally redeposit onto the dishware as the water flows away.
That makes perfect sense.
But here is the critical catch, and this is why the actual procedure in the kitchen is just as important as the chemistry itself.
Right.
For these surfactants to even have a chance to play Red Rover with the grease, The pre-rinse water temperature must be tightly controlled.
Okay, yeah, I was actually reading the timeline in the research report, and it specifies that the pre-rinse stage, which is where the dishwasher is basically scraping off the bulk proteins and, the leftover bivalve debris from the oysters.
Right.
It says the water has to be kept between 110 degrees and 120 degrees Fahrenheit, which, to me, honestly sounds surprisingly low for a heavy-duty commercial kitchen.
It does seem counterintuitive.
Yeah, why not just blast the plate with boiling water right out of the gate? Doesn't extreme heat equal a cleaner plate?
That is a very common misconception, and it's a mistake that can permanently ruin commercial dishware.
Wait, really?
Yes. If the pre-rinse water is too hot, the proteins from the shellfish, or say the starches from leftover pasta, they will rapidly denature.
What does that mean in this context, like denature?
It means their molecular structure unfolds and hardens. They will literally cook right onto the surface of the plate.
Oh, wow. So you're actually baking the food onto the ceramic before the surfactants can even form their micelles to lift it away.
Exactly. So if a well-meaning new dishwasher turns that initial hose to scalding, because, they think they're being extra safe and thorough,
They are actually failing the protocol.
they're practically gluing an oyster to the plate.
That's wild.
The mechanical cleaning is a multi-stage physical process. You have to remove the bulk debris at a moderate temperature first. You have to allow the chemistry of the surfactants to work before you can ever safely ramp up the heat.
Okay, so the soap has grabbed the grease. The temperature was kept moderate so the proteins didn't cook. But if the water is only 120 degrees, how do we actually get all that suspended grease completely off the plate?
You need physical force.
Do they just turn up the heat in the same tank to finish the job?
Oh, they absolutely cannot do that.
Right.
And that's where the FDA steps in with some very strict mechanical constraints.
Okay.
Once you move from the pre-rinse to the main mechanical wash cycle, the food code requires specific physical engineering inside the machine.
To make sure the dirty water holding all those micelles doesn't cross over into the clean phases.
Exactly.
Right. Looking at the FDA data, they mandate specific physical curtains or internal baffles inside the warewashing machines?
Yes, the baffles. There are physical barriers there to prevent internal cross-contamination between the wash tanks and the rinse tanks.
Because you absolutely do not want the water holding all that suspended greasy soil splashing over into your final fresh sanitizing rinse.
No, that would defeat the whole purpose.
And the physical force inside that machine is regulated too, isn't it? Like, the FDA mandates a very specific flow pressure for the water jets.
They do. The machine requires a flow pressure between 35 and 200 kilopascals, which translates to about 5 to 30 psi.
Why such a specific window, though? Why not just blast it at like 100 psi, like a power washer, to guarantee everything comes off?
It's a delicate thermodynamic balance.
Okay.
You need enough physical pressure to create shear force, literally pushing the suspended soils off the plate. But if the pressure is too high, the water jets atomize the water too finely.
Oh, it turns from a solid stream into a fine mist.
Exactly.
And a mist is bad.
A mist is terrible for this process because you lose the thermal mass needed to heat the surface of the plate.
Ah, I see.
A heavy droplet of hot water transfers heat. Well, right. But a tiny atomized mist cools down way too quickly as it travels through the air. And during this main wash cycle, you finally need that heat.
Right, because for stationary rack or conveyor machines, the temperature has to hit between 150 and 160 degrees Fahrenheit.
Correct.
Okay, so we need heavy, hot droplets. And while that 160-degree heat is blasting, the sources mention these automatic titration pumps, which basically act like a robotic bartender, right?
That's a great analogy.
Ah.
They're constantly measuring the water and injecting the exact right amount of detergent concentration.
So nobody's just guessing.
Exactly.
Mm-hmm.
It's entirely automated to remove human error so the chemistry stays perfectly balanced.
So let's review where we are for a second. The plate has been pre-rinsed at a moderate temp so the proteins don't cook.
Yep.
The surfactants have formed their micelles and trapped the grease. The internal baffles kept the dirty water segregated. And the pressurized, heavy 160-degree water droplets blasted the soil away.
Right.
So the plate is completely physically clean.
It is physically clean to the eye, yes. But it is not truly safe yet.
Right. And that brings us to sanitization. Because you can physically remove all the grease you want, but if there are invisible pathogens left behind from a raw oyster, someone is going to the hospital.
Oh, absolutely.
Now, our sources mention two paths here. Option A is thermal sanitization. This requires a fresh hot water rinse entering the machine manifold at a blistering 180 degrees Fahrenheit for most machines.
Yeah, thermal sanitization relies entirely on extreme heat to destroy microbial life.
Huh.
The intense temperature literally breaks down the cell walls of the bacteria.
That makes sense.
But a lot of kitchens simply don't have the heavy-duty electrical or gas infrastructure to keep water at 180 degrees all night long.
Right. That's expensive.
Very. So they use option B, which is chemical sanitization. This is very common in lower temperature machines or manual 3-compartment sinks.
And this is where my mind was completely blown. I always just assumed chemical sanitization meant you dunk a plate in some bleach water and call it a day.
Not at all.
But looking at the FDA food code, this is like a high-security combination lock. You need the exact right temperature, the right pH, the right concentration, and the right contact time.
That combination lock analogy is spot on. If just one of those 4 tumblers is off, the lock doesn't open, the sanitization fails, and the bacteria survive.
Which is terrifying.
It is. The FDA criteria for chemical sanitizers are an incredibly intricate balancing act.
So let's look at chlorine solutions as an example, because this is where the math gets wild.
Mm-hmm.
The FDA has this massive sliding scale, and I noticed a clear trend looking at the charts.
Okay.
It seems like if the pH of the solution is lower, you don't need the water to be as hot to get the same sanitizing effect. Why is that?
It comes down to mathematically mapping the chemical reactivity of the chlorine. When you put chlorine in water, it forms different compounds based on the pH level.
Okay.
In a more acidic environment, meaning a lower pH, the chlorine is forced to convert into hypochlorous acid.
Hypochlorous acid.
Yes, and hypochlorous acid is a hyperactive, incredibly aggressive killing agent.
Mm-hmm.
It punches through bacterial cell walls very easily.
Oh, wow.
So because the chemical itself is so aggressive at a lower pH, you don't need to add as much thermal energy, as much heat, to achieve the necessary bacterial kill rate.
That explains the FDA's math perfectly, because the code says if you have a chlorine concentration of 50 milligrams per liter and your pH is a highly alkaline 10, you have to keep the water at a minimum of 100 degrees Fahrenheit.
Right.
But if you drop that pH down to an acidic 8, the required water temperature plummets to just 75 degrees. The chemical is doing the heavy lifting instead of the heat.
Precisely. You are balancing the chemical aggression with the thermal energy.
But even if you have those 3 numbers perfectly dialed in, the pH, the concentration, and the temperature, you still have the 4th tumbler of the combination lock, time.
Time is crucial. Contact time is non-negotiable. For chlorine, it must remain in wet contact with the surface of the dish for at least 10 seconds.
What actually happens in those 10 seconds?
The sanitizer is achieving what we call a log reduction in bacteria.
Log reduction.
Yeah. When public health is on the line, killing 90% or even 99% of bacteria just isn't good enough. A log reduction is a mathematical term for decimating a population.
Okay.
A 5-log reduction, which is standard for sanitizers, means you are killing 99.999% of the harmful microorganisms. It takes physical time for the hypochlorous acid to breach the cell walls and ensure that 99.999% kill rate.
It's just dizzying to think about. And that's just chlorine. If a kitchen uses an iodine solution instead, the lock changes completely.
Entirely new rules.
Yeah, the pH has to be 5.0 or less, and the temperature drops to 68 degrees. Or what about quaternary ammonium compounds? The sources refer to them as quats.
Right. Quats introduce completely new variables. For quats, you need a minimum of 75 degrees Fahrenheit and a much longer contact time of at least 30 seconds.
30 seconds is a long time in a busy kitchen.
It is. And they are highly sensitive to water hardness. You can generally only use them in water with a hardness of 500 milligrams per liter or less.
Because the minerals in hard water physically interfere with the quat's ability to bind to the bacteria, right?
Exactly. The minerals basically get in the way.
So what does this all mean for the person actually working back there? It means the dishwasher isn't just splashing soap around. They are actively managing a complex chemical matrix.
Whether they realize it or not.
Right. And if the municipal water supply suddenly pushes harder water after a rainstorm, or the restaurant's water heater drops by just 5 degrees, the entire sanitization process can quietly fail without anyone even realizing it.
Which is exactly why the research report emphasizes a strict quality assurance phase. You need daily chemical logs, sanitizer test strip verifications, and calibration schedules for those dosing pumps.
You literally have to verify the math every single shift.
Every single one.
And you really want to verify it, because
Yeah.
if I'm listening to this and I've ever worked in a restaurant, I'm probably sweating right now thinking about all the times I just, blindly mixed floor cleaner with dish soap trying to get something clean faster.
Oh, that happens all the time.
But according to the safety data sheets in our sources, a simple chemical mix-up in this environment can result in literal toxic gas or explosions.
It's no joke. We are dealing with industrial-grade oxidizing agents, caustic bases, and strong acids. Mixing them blindly is incredibly dangerous.
Let's look at some of these specific reactions from the data set. Let's say a kitchen uses a standard chlorine sanitizer,
Okay.
and a well-meaning dishwasher notices some hard water lime scale building up on the inside of the machine. So they grab a delimer, like Keystone Limeaway, which contains strong nitric and citric acid.
Very common scenario.
Right. What happens if those two mix in the sink?
That is a critical chemical incompatibility. Mixing a chlorine-releasing agent with a strong acid instantly shifts the chemical equilibrium and generates toxic chlorine gas.
And the datasheet says the emergency exposure action for that is evacuating the area immediately upwind and seeking emergency medical attention for potential delayed pulmonary edema.
Yeah, chlorine gas is a severe pulmonary irritant. It attacks the mucous membranes and fills the lungs with fluid,
Oh my God.
and the threshold for danger is shockingly low. OSHA sets the ceiling limit at just 1 part per million in the air.
That is nothing. Okay, here's another one. Machine warewashing detergents. This stuff is heavily caustic, containing sodium hydroxide. What happens if this highly alkaline detergent comes into contact with reactive metals like an aluminum baking sheet or a piece of zinc?
That creates another severe hazard. That specific reaction rapidly generates highly flammable hydrogen gas.
Hydrogen gas.
Yes. Not only is that an explosion risk if it accumulates near, say, the pilot light of an oven, but the reaction itself causes violent exothermic splatter.
Wait, exothermic splatter.
It releases intense, instantaneous heat. It can boil the localized liquids right on the surface of a metal, shooting highly caustic, boiling soap back into the dishwasher's face.
Causing severe thermal and chemical burns.
Precisely.
That is terrifying, but it isn't always about explosions or toxic gas, is it? Sometimes a mix-up just quietly destroys your ability to keep the kitchen safe.
Very true.
Take quat sanitizers. This is a very common low-temperature sanitizer for the third sink. What happens if a dishwasher accidentally mixes it with standard liquid pot and pan detergent?
This is a classic and very problematic reaction. Most standard foaming dish soaps are anionic surfactants, meaning their active cleaning molecules carry a negative electrical charge.
Okay, negative charge.
But quaternary ammonium sanitizers are cationic. Their active molecules carry a positive charge.
Oh, so it's like putting a magnet on a refrigerator.
That is exactly what happens. The positive and negative molecules are so strongly attracted to each other that they bind together instantly.
Wow.
This causes a total chemical neutralization. They lock together so tightly that they can't do anything else.
So if a hardworking dishwasher decides, hey, this pot soap works great and this sanitizer works great, I'm going to mix them together in the sink and get double the cleaning power. They aren't making a super soap.
Not at all.
They're creating a useless, inactive sludge. Suddenly, your expensive sanitizing chemicals are just heavy, deactivated complexes sitting in the bottom of the sink.
Leaving the kitchen completely vulnerable to bacterial growth.
Yeah.
And if we connect this back to the bigger picture, this is exactly why the FDA Food Code explicitly mandates that newly installed machines must be equipped to automatically dispense detergents and sanitizers.
The code says they literally have to incorporate visual indicators to verify delivery or an audible alarm to signal if the chemicals aren't feeding correctly.
Yes, because you simply cannot rely on a human being, no matter how well-meaning, to perfectly measure out a complex matrix of incompatible, highly reactive chemicals during a chaotic Friday night dinner rush.
You just can't.
The automatic pumps ensure the right chemical goes in at the exact right moment, at the precise FDA-mandated concentration.
It is an incredible, invisible ecosystem operating right behind the kitchen doors. I mean, every time you eat off a perfectly clean, spot-free plate at a restaurant, you are benefiting from this astonishing orchestration of surfactant micelle formations, exact pH balances, and split-second chemical timing that kept you safe.
It really gives you a profound appreciation for the engineering and the applied science that forms the backbone of public health.
It really does. But before we wrap up, it leaves me with one final provocative thought.
Let's hear it.
Looking at the sheer danger of these chemicals, the constant risk of toxic chlorine gas, the exothermic splatters, the heavy caustic residues, what does the future of sanitization actually look like? Are we going to be using these dangerous oxidizers forever?
That is a very important question for the industry. And there is a small hint of where things might be going right in our sources.
Yeah, I noticed at the very bottom of the chemical list, there's a product called Pathways Drain Treatment. And unlike the harsh acids or the dangerous chlorine, this product's active ingredients are listed as viable bacterial cultures, spore blends, and enzyme systems like protease and lipase.
Right, it's biological grease digestion.
Yeah.
Instead of using a harsh chemical solvent to aggressively break down the organic waste, it uses living, targeted organisms to literally eat it.
Exactly. So my question for you, the listener, is this. Could the commercial dish pit of the future move away from these hazardous, explosive chemical combinations entirely?
It's entirely possible.
Like, could we replace the caustic alkaline salts and the toxic chlorine gas with vats of bioengineered living enzymes designed to just eat the grease right off our plates while we wait?
It's a very compelling idea, moving from synthetic chemistry to biological engineering. But as we've explored today, whatever replaces the current system will still have to answer to the strict, unforgiving mathematics of the FDA code.
So true. Well, next time you are sitting in your favorite seafood restaurant and you hear the clatter of plates and the hiss of steam coming from the back room, just remember, you aren't just listening to dishes being washed, you are listening to a high-stakes chemistry lab working perfectly right on the razor's edge.